History
All right, up to this point, we've been looking at a horizontal oscillator, a block oscillating back and forth due to a spring. It's sitting on a frictionless surface, and we used a plausibility argument to say that the position of the block at any point in time is a cosine omega t plus phi, right? All right, so that we did that with a plausibility argument. Today, what we're going to do is actually apply Newton's second law and actually take a look at the solution to this problem where we have this oscillator. Is this indeed the position function? Let's take a look. All right, let's just apply Newton's second law. It's pretty straightforward, actually. Circle the object of interest when it's there, and we got position, and there's our object. To model it as a particle, we got the weight down, we got the normal force up, and it looks like we have another contact force. In this case, we have a force of a spring this way. All right, so we can apply Newton's second law. We'll say sum of the forces in the x equal mass times the acceleration, right? The y forces are balanced. There's no acceleration in the y direction. So we got that. So we end up with the spring force, which is in the negative direction, is negative kx, using Hooke's law, equals m. And what we're going to do is set up a second order differential equation in terms of x. So this is d squared x dt squared. We're going to take the second derivative of position to get, and because that's acceleration. All right, so we end up with that. We end up with a second order differential equation. Let me just rearrange this a little bit and just say k over m x equals d squared x dt squared. All right, so we said that's the answer, right? We said that's the answer. So is that the answer? Is this the solution to this differential equation? Now, the solution to a differential equation is a function, different than like just a regular algebraic equation where the solution, once you get your parameters in, is usually a number. But the solution to a differential equation is going to be a function. So our argument thus far has been that's the solution to this motion. So why don't you take a moment and see, is this indeed the solution, right? So all you really need to do is plug that in. We say that's x, plug that in there, take the second derivative, plug that in there, see if they're equal. All right, why don't you take a moment to do that?
Pause the video now.
It turns out this is the solution to that differential equation. Under what? Under one condition. Do you know what that condition is? Right? What's the condition under which this is a solution to that? What's the condition? Under what circumstances is this the solution? Well, hopefully you figured that out. Hopefully you looked at it and go, oh, it is, if this is true. Let's take a look. All right, so all I got to do is, to see if it is, I'm going to plug this in here. So I end up with minus k over m a cosine omega t plus phi, right? I just substitute. I didn't do anything fancy here. The second derivative of this, well, the first derivative, of course, velocity, is negative a sine omega t plus phi. And then the second derivative, d squared x dt squared, of course, which is acceleration, is minus, oh, that's not right. Not a sine, it's a omega, minus a omega sine, right? I didn't use the chain rule there. I got to have that in there. All right, so minus a omega squared cosine omega t plus phi is the second derivative, right? And keep in mind, That's the maximum speed of this oscillator, and that's the maximum acceleration. All right, well, let's plug that in. And so this is the second derivative, and it's minus a omega squared cosine omega t plus phi. All right, are they equal? Because they have to be equal if that's the solution. Are they equal? Are they equal? Well, yes, under one condition. And hopefully you can see that condition, right? This is true if and only if omega squared equals k over m, right? Because these two are the same if omega squared is k over m. And as we saw when we did our energy analysis, omega equals the square root of k over m, right? We got that already. All right. So, and indeed, this is true. So this is the solution to the differential equation, right? This was like a guess and check technique. In differential equations, we do that a lot. Some aren't explicitly solvable. There's no real technique to solve them. So differential equations often model physical systems, and we know how the physical system behaves. So we have an idea what the solution is, so we can guess and check it. And in this case, we guessed the answer, and we checked it, and it is indeed the answer, and it is the unique answer to this differential equation. You might find that a little distasteful technique, but get used to it. Once you study the differential equations, this sort of things are going to come up frequently. All right, so there you go. There's the, this is indeed, so we applied Newton's second law, and we saw that this is indeed the solution to the differential equation, as long as that's the angular frequency, and we demonstrated that was true with energy. All right, now this is called the equation of motion, and it's of the form minus some constant times x equals d squared x dt squared. Right? That is the equation of motion. Anytime you see something, an equation of that form, if this is a position function, this is describing something in simple harmonic motion. Always, whenever you see an equation of this form, some constant, some constant times position, and this has to be a different sign than this, equals the second derivative of that thing with respect to time, then this thing is in simple harmonic motion anytime you see this of this form. What is the significance of C in this case? What is C? Why don't you take a moment, see if you can figure out, if I see this, what does C represent in this case, right?
Pause the video now.
This represents a simple harmonic oscillator, right? Where we can look at this and we could see that in this case, C took the place of K over M, right? So therefore, C equals omega squared, right? C equals omega squared. In this case, C was this, and omega is the square root of this, so C equals omega squared. So anytime we see that, we see an equation of this form, we know that this constant is the square of the angular frequency. That will always be true, right? And you have to be able to identify that. So let's take a look at a problem. Let's say we had a function that looked like this. We had a function that looks like that. We got a position function like this. Number one, describe the object's motion. And number two, what is the period of oscillation, right? So, I want you to take a moment. Describe the motion, and what is the period of the oscillation?
Pause the video now.
All right. So, this is simple harmonic motion. This is called the equation of motion. This is of the form, this is the equation of motion. Minus cx equals d squared x dt squared, right? And this is of that form. So in this case, we have 9 equals omega squared, right? So omega equals 3 in this case, equals 2 pi f equals 2 pi over the period. Right, omega equals that, 2 pi f or 2 pi of the period. So therefore, the period equals 2 pi over 3. Right? So this is a simple harmonic oscillator with a period of 2 pi over 3. Right? If it's in standard units, that would be in seconds. All right. So there you go. So now we've actually demonstrated this is true with physics, which is, you knew we were going to have to do that eventually. With an ideal spring, we have what's called a linear restoring force, right? We got Hooke's law that says F equals minus K delta X. And this is a linear restoring force. So linear in that we're just multiplying the displacement times a constant, and that will give us the force. And restoring means that whenever I move away from my equilibrium position, if I move this way, the force is always going to try and get me back to the equilibrium position. If I compress it, the force is this way, and if I stretch it, it's this way. That's what that negative sign is about. So this is a linear restoring force, right? Linear because the force is directly proportional to the displacement in the opposite direction of the displacement. Anytime we have a linear restoring force and we disturb that thing from its equilibrium position and release it, it will go into simple harmonic motion, and this could describe its motion, right? It will be sinusoidal, simple harmonic motion, and it could be described with the equation of motion. That is a general relationship. Okay, so that's an important to know too. We got to keep an eye out for these linear restoring forces because they rear their heads in very strange times. We'll have a problem later where we drill a hole through the earth and go, oh, look, linear restoring force. And then we'll know we're in simple harmonic motion. All right, so there you go. We've proven that is the position function. All right. Make sure you can drive all this stuff. This unit, it's very important to be able to derive these things, see how these all work together. We got a lot of relationships. Don't try and memorize your way through that. Derive your way through it. You'll be able to remember it easier, right? So make sure you're doing that. Catch you later.
Extreme physics.